As the filtrate is formed in the capsular space, the capsular pressure, or pressure due to the fluid, increases. It cannot go back into the blood, so it's forced out the only exit, the proximal convoluted tubule. As the filtrate passes through the renal tubules and the collecting ducts, reabsorption and secretion between the blood and filtrate will occur. The walls of the renal tubules have pores, channels, and pumps that allow for fine-tuning of the filtrate. As illustrated in this image, facilitated diffusion and active transport can occur across the walls of the renal tubules. Most of the reabsorption actually occurs in the proximal convoluted tubules. Organic nutrients that were small enough to be filtered out will be reabsorbed here. These organic nutrients include glucose, amino acids, and fatty acids. Their reabsorption across the walls of the renal tubules uses facilitated diffusion and active transport. Active reabsorption of ions or electrolytes also occurs in the proximal convoluted tubules. Sodium, potassium, magnesium, bicarbonate, phosphate, and sulfate ions are reabsorbed using ion pumps. As we discussed earlier, ion pumps, including sodium and potassium pumps, may be influenced by hormones. Angiotensin II, for example, stimulates sodium reabsorption. In addition, the massive reabsorption of water that is necessary occurs in the proximal convoluted tubules. Secretion also occurs. Additional hydrogen ions, for example, can be secreted in response to pH. If the blood pH is too acidic, the excess hydrogen ions can be secreted into the proximal convoluted tubules and flushed down the toilet. Glucose is actually filtered across the filtration membrane. As we discussed in metabolism, glucose is an important nutrient used to synthesize ATP. There are transport proteins in the proximal convoluted tubules, in the walls of the proximal convoluted tubules, that transport and reabsorb the glucose back into the blood. Under normal conditions, there should be little to no glucose in the urine. Elevated urine glucose levels are called glucosuria. Now, usually we test under fasting conditions. If I happen to eat a very large slice of decadent chocolate cake and test my urine shortly after, I will most likely see elevated urine glucose levels. This is not surprising nor abnormal. The excess glucose that flooded my bloodstream after eating the big chocolatey slice of cake, I can dream, can't I? It can overwhelm the transport proteins. So if there's too much in the blood, the transporter proteins cannot move it all back fast enough, and some will spill out in the urine. It's rather like trying to bail a big sinking ship like the Titanic with a small bucket. Good luck. This is why we see elevated urine glucose levels in diabetics, even when they're fasting. Because they do not have enough insulin or the insulin receptors are not working, glucose cannot move from the blood into the cells. It therefore stays in the blood and spills out with the urine. There is a rare genetic disorder where the glucose transport proteins in the renal tubules are absent or do not work. In these patients, the glucose is filtered out in the renal corpuscle, just like normal, but it cannot be reabsorbed. It's all going down the toilet. This makes their lives exceedingly challenging. They're not able to retain or store glucose. They must have a constant supply in order to maintain their blood glucose levels for brain function. In extreme cases, they may need IV or feeding tubes while they sleep because they cannot go for more than a few hours without ingesting carbohydrates. So filtrate flows from the proximal convoluted tubule down the loop of Henle into the distal convoluted tubule. The loop of Henle is primarily involved in concentrating the urine to control blood volume and pressure. I'm going to talk about that process in just a minute. first I want to skip ahead to the distal convoluted tubule. This is where most of the final touches on solutes in the urine are done. The distal convoluted tubule plays a big role in calcium homeostasis. Parathyroid hormone and calcitonin, two hormones, both act on the distal convoluted tubule to regulate plasma calcium levels. Now remember, calcium is not only needed for bones, but it's also required for muscle contraction. Just like glucose for the brain, blood calcium homeostatic levels are critical for skeletal muscle fibers, smooth muscle fibers, and cardiac muscle fibers. If the blood calcium levels go too high, calcitonin is released and causes calcium secretion in the distal convoluted tubule. The excess calcium is flushed down the toilet. If the plasma calcium levels are too low, parathyroid hormone is released. Parathyroid hormone causes calcium reabsorption in the distal convoluted tubule. The calcium is reabsorbed back into the blood to maintain the plasma calcium levels. Elevated potassium levels can also be very dangerous. So the distal convoluted tubule can secrete excess potassium. The distal convoluted tubules can also continue to secrete hydrogen ions to help regulate blood pH. As we discussed in metabolism, ammonia generated by deamination of the liver is toxic. The distal convoluted tubules can help with this. They can secrete the ammonium ions. The very last tube that can do any secretion or reabsorption is the collecting duct. Once it passes the collecting duct, whatever is in the filtrate will go into the toilet. The collecting duct can reabsorb sodium ions. Even though sodium has a bad rap from the American diet, it is necessary in the extracellular fluids to maintain the cellular transmembrane potentials and for neuronal action potentials. Bicarbonate can be reabsorbed to, again, help regulate blood pH. Bicarbonate's a weak base that can act as a buffer. Urea can also be reabsorbed. Urea can play a role in the countercurrent exchange system in the loops of Henle that allows for reabsorption of water. Remember, we need to reabsorb over 100 liters of water per day. And then depending on blood pH, is it too acidic or too basic, hydrogen or bicarbonate ions can be secreted. To summarize, filtrate is formed during glomerular filtration in the renal corpuscles. From the capsular space, the filtrate flows through the proximal convoluted tubules, down the loops of Henle, through the distal convoluted tubules into the collecting ducts. What happens as it passes through the loops of Henle, and why do I have a picture of army tanks here? All right, small tangent. Many of my family members and friends are or were in the military. A very good friend of mine is in the Army. He was, he was deployed during Desert Storm, where he was a tank operator. He did come back with many stories, but one relevant to this discussion is about water conservation. Now, please forgive me if I'm not using the terms exactly correct. I actually grew up as an Air Force brat. So his platoon or company had a medic, and the medic would administer a daily field test. To pass the field test, my friend had to pee in a cup. The medic would look at the urine to see if he passed. What was the medic looking for, and what would happen if my friend failed? The medic was looking at the color of his urine. It has to be colorless or minimally light yellow. If it was dark yellow or orange, my friend failed. And if he failed, not only could he be kicked out of the Army, but he could also be brought up on charges. What was so important about the color of his urine? The medic was checking to see if my friend was drinking enough water. It's very hot and dry in the desert, and they were exercising a lot. So if he was not drinking enough water, he could become dehydrated. Many people don't actually feel thirsty until they're already dehydrated. In an adult, dehydration can lead to fatigue, dizziness, and confusion. All three of these are very bad during combat situations and while operating a multi-million-dollar machine. If he became dehydrated, what were the charges that he could be brought up on? He could be charged with destruction of military property, and I'm not talking about the tank. If you are in the U.S. military, they own you. Your body is considered their property. This is also why certain military professions are banned from riding motorcycles. This is an extreme example, but it emphasizes the importance of water conservation by the kidneys. Remember, filtration is based on size only. Metabolic wastes, water, and small solutes, including ions, electrolytes, glucose, fatty acids, amino acids, and vitamins, will be filtered out. Filtration pressure forces the filtrate into the capsular space. From the capsular space, the filtrate flows into the proximal convoluted tubule. The walls of the proximal convoluted tubule are semi-permeable, and most of the small solutes, glucose and water, will be reabsorbed. From the proximal convoluted tubule, the filtrate will flow through the loop of Henle, down the descending limb, and up the ascending limb. The walls of the ascending and descending limb are different. That's why one is drawn thinner and the other is thicker. The ascending limb has sodium chloride pumps that use ATP to pump sodium and chloride out into the peritubular space surrounding the loop of Henle. Because the pumps use energy, the sodium and chloride can become very concentrated down the medulla where the loops of Henle are. The walls of the descending limb have aquaporins, making them permeable to water. So as the filtrate flows down the descending limb, the water leaves the tubule to try and dilute the sodium and chloride. The sodium and chloride and water are reabsorbed into the capillaries of the vasa recta. From the loop of Henle, the filtrate will then flow into the distal convoluted tubule and down the collecting duct. Now let's look at the same process using numbers. This diagram is showing osmolarity of the filtrate. Osmolarity is a measure of concentration. Bigger numbers mean more concentrated. Smaller numbers mean less concentrated. Zero osmolarity is distilled water that has no solutes. It only contains H2O water molecules. So from the proximal convoluted tubule, the filtrate flows down the descending limb of the loop of Henle. As it flows down, water leaves through the aquapores. As water leaves, the osmolarity increases. The filtrate becomes more concentrated. It has less water with the same amount of stuff. The filtrate then flows up the ascending limb. As it flows up, the pumps use ATP to push sodium and chloride out. Because the pumps use energy, they can make the sodium and chloride in the regions around the loops of Henle really concentrated. And because the descending limb is actually, because the descending limb, one going down, is actually also permeable to sodium and chloride, these ions move down their concentration gradients back into the tubule. They get caught in this loop, out the ascending, in the descending, out the ascending, in the descending, over and over again. This loop of sodium and chloride keeps the concentration surrounding the loops of Henle high. And this drives water out of the descending limb so it can be reabsorbed by the vasa recta. Again, if we look at the osmolarity of the filtrate as it travels up the ascending limb, it becomes less concentrated, more dilute. If we compare the filtrate as it enters the loop of Henle and it exits the loop of Henle, the osmolarity decreases. You normally urinate dilute urine. This is why, if you're properly hydrated, urine should be clear or light yellow. But wait, the title of this section was water conservation. What happens if you don't drink enough water? How do your kidneys retain water to prevent dehydration? First, remember this is a two-dimensional diagram. This two-dimensional diagram is trying to illustrate a process that is in a three-dimensional organ, the kidneys. So the sodium chloride pumps line the walls of the entire ascending limb. The front, the back, the sides, all the way around. The high concentration of sodium and chloride goes all the way around the tubules in the renal pyramids. And the filtrate flows from the ascending limb into the distal convoluted tubule and down the collecting duct. The collecting ducts run parallel or alongside the loops of Henle. Under normal let me start over, my tongue just got tied. Under normal conditions, the concentration of the filtrate from the ascending limb through the distal convoluted tubule and down the collecting duct does not change much. However, if the body becomes dehydrated, antidiuretic hormone will be released. Antidiuretic hormone acts on the collecting ducts. It opens aquipores in the walls of the collecting ducts. Now, as the filtrate flows down the collecting duct, water wants to leave so it can dilute the sodium and chloride surrounding the tubes. As the water leaves the collecting duct, the filtrate becomes more and more concentrated. With ADH, you will reabsorb additional water and urinate concentrated urine. So where does this additional water go? Where is it reabsorbed to? Remember, the loops of Henle and the collecting ducts are surrounded by the capillaries of the vasa recta. The water that is being reabsorbed, water that is leaving the tubes, the loops of Henle, and the collecting duct will go into the vasa recta and be carried by the veins out of the kidney to the rest of the body. So remember, there are two types of nephrons, juxtamedullary nephrons and cortical nephrons. Cortical nephrons have very short loops of Henle and are located higher in the renal cortex. The cortical nephrons are primarily responsible for filtering toxins and wastes from the blood. Juxtamedullary nephrons have very long loops of Henle that dip way down deep into the pyramids of the renal medulla. The long loops of Henle make the juxtamedullary nephrons really good at creating big concentration gradients. This allows them to really concentrate the urine. As the loops of Henle dip down into the renal pyramids, they're surrounded by the capillary beds of the vasa recta. Water leaves the loops of Henle, or as the water that leaves the loops of Henle and the collecting ducts, it is reabsorbed into the vasa recta. From the vasa recta, it's then carried out of the kidneys, in the veins, to the rest of the body. Once the filtrate leaves the collecting ducts, there is no more change to the fluid. It's now officially urine. Urine flows from the collecting ducts to the papillary ducts, to the minor calyces, to the major calyces, to the renal pelvis, down the ureters, and into the bladder. The bladder is a temporary holding tank. As the bladder fills with urine, stretch receptors in the detrusor muscle will send signals up the spinal cord. The integrating center for the micturition reflex is the sacral region of the spinal cord. Now remember, micturition is the anatomical term for urinating or emptying the bladder. And the micturition reflex will relax the sphincters of the urethra. So an adult bladder can hold around 800 milliliters. It very rarely, however, fills to capacity. The stretch receptors are actually stimulated around 200 to 400 milliliters. This reflex prevents the bladder from overfilling and rupturing.